Hi, I'm Chris Jensen, a first-year PhD student at the University of Cambridge. As I'm sure you all know, many of our cloud systems use strongly consistent databases for coordination. This talk is specifically looking into how we think about these kind of systems and whether it's correct to think of them simply in terms of their underlying protocol. We're specifically going to be looking at Raft, which is a strongly consistent log replication protocol, which means that every server which runs it will have a shared replicated log, which you can then run a state machine on top of. And all servers will report the same result at each step. One use case for this is in databases, and a variety of open source projects use Raft, such as Titanium Key Value Store, Yugabyte DB, Console, Cockroach DB, and most relevant for this talk, etcd. For reference, etcd bills itself as a highly available key value store and is used in projects such as Kubernetes or OpenStack. So, what does highly available actually mean in this context? So, pulling from their documentation, a etcd cluster will operate so long as a majority quorum can be established. This implies that so long as a majority of your nodes can communicate, your cluster should continue to function. Since etcd provides a highly available key value store, it can be used simply for that. One place where it's used in this fashion is at Cloudflare, where they use it to manage their control plane. However, this usage led to a 6-hour outage in November last year, where despite redundant network switches and multiple distributed nodes, a partial failure in one of the switches caused the cluster to become unavailable. So why did this failure occur when we can see on the right that there should still be a majority of quorums that can be established? Useful here to dive into how etcd via Raft provides this guarantee. So Raft works by first electing a leader, which can then replicate requests from clients. If a node believes the leader has crashed, it will start a leader election, so in this case B starts a leader election, and sends election requests to the other nodes. The other nodes will vote for the candidate if the candidate's log is longer than their own. Additionally, when nodes receive this election request, they will stop responding to previous leaders. Once a candidate has received votes from a majority of nodes, it becomes the leader and then can replicate requests. Once a request is replicated to a majority of nodes, it is committed and can be acknowledged to the client. However, what is important to note is that once a leader election has started, the previous leader can no longer replicate requests. And as a result, in every leader election, there is a period between when the election starts and when the leader is elected, where no request can actually be processed. So let's run through Raft with regards to full and partial partitions. So considering first a full partition, we can see that B and C form a majority quorum, so etcd should be able to function normally. However, when we think about a partial partition, although we should still have the same majority quorum, it can interfere with that. So if we assume here that B is initially the leader, when the partition is in place, since A does not hear from B, it believes the leader is dead and will start an election. When this election message reaches C, it blocks C from responding to any previous leaders, for example B. However, because A has an older log than C, C will not vote for it because B will have replicated some entries to C. Then B will no longer be able to replicate any entries to C and will step down. Since the cluster has no leader, an election will take place and either B or C could be elected. If C is elected, it can communicate with both A and B, and so A will not time out in the election. While if B is elected, we're in the same as our initial state, and so this will repeat several more times until C is elected. So how can we test these kind of scenarios? Well, we could physically replicate Cloudflare's setup. However, this would be potentially difficult and expensive to do. Alternatively, we could emulate a wide range of possible deployments with the tool we've been developing called Reckon. The idea behind it is that we can emulate the network using Mininet and insert etcd nodes and clients into that, as well as injecting failures into the network. So what would we expect in terms of success rate from Raft during one of these partial partitions? In the graphs from here on out, we have 20 seconds of initially of a normal network, followed by 20 seconds with a fault injected, and then finally 20 seconds of a normal network again. What we'd expect is that during the initial normal network, we have no problems. It's the steady state. Then when the partition is injected, soon after, A will start an election, blocking C from processing B's request and forcing either B or C to be elected. This should repeat several times until C is elected leader. From then on, the partition won't affect the cluster. However, what happens in etcd is quite different. So rather than the repeated leader elections throughout the partition, we only see a single election afterwards. Additionally, we have partially degraded performance throughout the partition. If we examine etcd's logs during the partition, we see that although A initiates many elections, C explicitly ignores these due to what's called the check quorum optimization. This essentially says that if the cluster is stable, node should avoid disrupting it. When implemented in etcd, this means that followers with a stable leader will ignore election requests. Thus, when the partition is removed, the election request finally arrives at B, which will then step down, causing the leader election, which either B or C can win. The question then is, why is there this degraded performance during the partition? Rather than etcd sending requests directly to the leader, it dispatches requests in a round-robin fashion to each node. If the receiving node is not the leader, it attempts to forward the request onto the leader, and so considering the destinations for requests, if a request goes to B, B being the leader, it can be immediately processed. If it goes to C, well, C can communicate with B and so can forward the request directly to B. However, if a request goes to A, since A thinks the leader has died, it cannot forward the request. Thus, the request will time out on the client and be retried against one of the other nodes where it quickly returns. So this shows up as about a third of requests during the partition being delayed by several seconds, and because we're using a success rate timeout lower than that, we have lowered success rate during the partition. Since this doesn't show the repeated leader elections described in the Cloudflare postmortem, a hypothesis is that they had an intermittent partial partition and hence had many rapid iterations of this injection removal, resulting in a lot of downtime due to the leader election when the partition is removed. The question then is whether there is a solution to avoid the leader election after the partial partition. The answer is yes, and this is called the PreVote optimization. It has been implemented in etcd, however, is disabled by default in the current version and will be enabled in upcoming versions. So essentially, it requires that before a node can call a leader election, it first checks that it could actually be elected. So in this case, A would send out its pre-vote messages to B and C. The request to C would be rejected because C would not vote for A. As a result, A knows it could not be elected and thus doesn't start the elections, which disrupts the cluster. Looking at the graph here, we can see that when the partition is removed at 40 seconds, we don't have the leader election. However, we still have the problem of a third of requests being delayed. In conclusion, when partial partitions are concerned, the behavior of etcd is quite different from that of Raft, and additionally in the paper we show etcd's behavior in several other scenarios. Finally, if you want to reproduce the results in the paper, Reckon is available on GitHub as well as an artifact evaluation repository. If anyone has any good ideas for systems or scenarios to test using the tool, let us know and we can work to integrate it in. In theory, we can test any situation which it is possible to emulate in Mininet. Thanks for listening. Any questions?